Welcome to Brain Vision.
In this problem, we're going to talk about Compton-scattering. So consider that we have an incoming photon that has a wavelength lambda, and this photon collides with an electron initially at rest, and the photon loses some energy in the collision, such that its final wavelength, lambda prime, is equal to the initial wavelength plus h divided by the mass of the electron times c times 1 minus the cosine of the scattering angle theta. Okay, so in our problem, we're going to consider Compton scattering happening in the sun. And what we have is that the initial photon emitted by the nucleus of the sun is emitted with an energy of 10 to the sixth electron volts, 10, that is 1 mega electron volt. And when we see the photons, they have a wavelength of about 500 nanometers. And in the meantime, the photon collides 10 to the 26th times. And our going question A is to find what is the average increment in the wavelength of the photon for each collision. So notice that the wavelength of the photon, when it's produced by the sun, I'm going to call it lambda, and the wavelength that we see, I'm going to call lambda prime. So lambda is hc divided by the energy of the photon. And this is true because the energy of a photon is hc divided by lambda. Hc is 1240 electron volts nanometers, and the energy is 10 to the sixth electron volts. So lambda is equal to 0.00124 nanometers. So the total increment delta lambda is lambda prime minus lambda. This is approximately 500 nanometers. It's equal to 500 minus 0.00124. I'm going to just round it up to 500 nanometers anyway. And since we have that the number n of collisions is equal to 10 to the 26th collisions, then the average increment delta lambda prime is equal to the total increment divided by the number of collisions. That's 500 nanometers, 500 times 10 to the minus 9 meters, divided by 10 to the 26th collisions. So this is equal to 5 times 10 to the minus 33 meters per collision. Very small increment that sums to be a very great increment in the end. Then in question B, we have to calculate what is the average value of phi, that is the average angle by which the photon is scattered, considering the process in question A. Now what I'm going to do is to write here that lambda prime is equal to lambda plus h over mc times 1 minus the cosine of phi. And notice that the final wavelength, actually, we'll call this here lambda tilde, and this lambda prime is the final wavelength, is equal to the initial wavelength plus the sum of the increments, the sum of overall collisions of the increments, h over mc times 1 minus cosine of phi. And we are assuming that phi is the same for all collisions. So the sum here is just the number of collisions times h over mc 1 minus cosine of theta. And here I'm going to assume that the cosine of theta is very, I'm sorry, the theta is very small. So cosine of theta is approximately 1 minus theta squared over 2. So lambda prime is lambda plus nh over mc times theta squared over 2. And since our goal is to find theta, we can find it by taking the square root of 2 times lambda prime minus lambda times mc over h, 1 over n. So this is the square root of 2 times 500 times 10 to the minus 9 meters divided by 2.43 times 10 to the minus 12 meters. And here I'm using that h over mc. This is a useful value to know, is 2.43 times 10 to the minus 12 meters. And then I have to multiply it by 1 divided by 10 to the 26th. So phi is equal to 6.41 times 10 to the minus 11 radians. And since the exercise wants the answer in degrees, I'm going to multiply it by 180 degrees and divide it by pi in order to obtain 3.67 times 10 to the minus 9 degrees. Then, in question C, we have to find what is the mean distance traveled by the photon inside the sun before it's scattered. Given that the time it takes for the photon to exit the sun is 10 to the 6th years. So notice that the average time it takes, I'm going to call it capital T, that the average time it takes for a photon to be scattered is equal to the total time t divided by the number of scattering events that happen inside the sun. So it's 10 to the 6th years, and I'm going to multiply it by 3600 seconds per hour times 24 hours a day times 365 days a year. Okay, and then divided by 10 to the 26th scattering events. Notice that the year cancel out the days and the hours, so only the seconds remain. So the time, the average time for a collision to happen is 3.2 times 10 to the minus 13 seconds. And now let's calculate how far a photon travels when it's free during this time of 3.2 times 10 to the minus 13 seconds. So the distance is the time times the speed of light. So that's 3.2 times 10 to the minus 13 seconds times 3 times 10 to the 8 meters per second. So d is equal to 9.6 times 10 to the minus 5 meters, which is the answer to our exercise.